By the mid-1800s, the laws of electricity and magnetism were considered complete. Engineers were already using them to build reliable telegraph networks and early power systems, treating the equations as finished tools for a functional world. Then, James Clerk Maxwell identified a subtle, entirely theoretical contradiction within these established laws, a mathematical inconsistency that had gone unnoticed by his contemporaries. Maxwell conducted this investigation as a thought experiment, treating the empty space of a charging capacitor as the site of a missing physical process. Maxwell's solution functioned as a necessary correction to the existing laws. This adjustment ensured the equations remained valid in every scenario, proving that changing fields are physical sources in their own right. Imagine a simple battery connected to a parallel plate capacitor. The moment the circuit is closed, current begins flowing through the wires to charge the plates. Under standard physics, we measure the magnetic field at point P by drawing an imaginary flat, circular loop around the wire. Ampere's law works because physical current passes through that loop's surface, resulting in a measurable, non-zero magnetic field at point P. However, the law allows us to change the geometry of that surface. If the surface bulges out into a pot-like shape, the rim stays at point P, but the closed bottom now sits in the empty space between the capacitor plates. Because no physical wire or moving charges pass through this new surface, Ampere's law claims the magnetic field at point P must be zero. This creates a contradiction. A single point in space cannot have a magnetic field and zero magnetic field at the same time. The existing law was missing a necessary term. To resolve the conflict, we have to look into the vacuum between the plates and ask what is crossing that gap. As charges accumulate on the plates, an electric field builds in the gap, measured as electric flux. Maxwell observed that a changing flux produces magnetic effects, allowing this pulsing electric field to generate a magnetic field identical to a physical wire. The rate of change of the electric field acts as the missing source. It provides the necessary magnetic influence within the vacuum of the capacitor. This formula represents the displacement current. It is proportional to the rate at which the electric flux changes over time. Conduction current flows through the wires, while the displacement current carries the interaction across the gap between the plates. The finalized Ampere-Maxwell law sums both currents. This ensures the magnetic field remains consistent across every surface we choose to draw. This addition resolves the circuit paradox, while confirming that time-varying electric fields generate the same physical effects as moving charges. This discovery mirrors Faraday's law, which established that changing magnetic fields create electric fields. Maxwell's displacement current completes a perfect physical symmetry. Changing electric fields likewise create magnetic fields. These fields can now sustain each other. One field change triggers the next, passing energy back and forth in an infinite loop through empty space. This symmetry allows electromagnetic energy to propagate across the vacuum of space without the need for a physical medium. Maxwell calculated the propagation speed of these self-sustaining field loops and found the result matched the speed of light exactly. Light, radio waves, and X-rays consist of these induction and displacement currents oscillating in tandem as waves. Years later, Heinrich Hertz experimentally confirmed that these invisible ripples existed in the laboratory. By resolving a minor inconsistency in a charging capacitor, Maxwell identified light as a continuous electromagnetic process.